All right, so our goal for today is to review for the first test. Test one covers, chapters 1, 2, 3, and 4. As I think we've talked about, the chapter that I cover right before the test, in this case, chapter 4, there's no credit quiz for that chapter, but there are practice quizzes. So you can still practice the material, and you should, right? Remember, those practice quizzes are worth a point apiece. So you do get points for doing them, but the practice quizzes are there for chapter 4. There's just no credit quiz. The main objective for you in the next 2 days is to prepare for exam 1. Exam 1 is set to open 12 a.m. Thursday morning and close basically midnight Thursday night. So you have all day Thursday to take it. You can pick when you want to take it, when it fits best into your schedule. And we will not be meeting for the Zoom sessions on Thursday. I'm not going to introduce a new chapter with you taking a test, right? So the only, and I don't want to say the only thing you have to do, it's a big thing. What you have to do on Thursday is take the test. So on Thursday, if you do have questions for me though, and you want to meet for Zoom, like a Zoom session before you take the test, just let me know, reach out and let me know if there's a time that's good for you. But otherwise we're going to go ahead and get started. I did just look at the exam really quick. I want to make sure I didn't forget to kind of look at everything. There are 36 questions. In the past, I had given 105 minutes. I went ahead and upped it to 120 because I think it's just typing stuff in. Sometimes when you type things in, it just takes longer than if you're doing a handwritten test. So you have 2 hours to take the exam, so definitely budget enough time. Make sure all of your mathematical problems that you do, you always report those with the right number of significant figures. I'm in the process of grading the credit 3 chapter 3 credit quiz. There we go. And it looks like most of you have done a great job with the chapter 3 material. Just make sure your final answer has the correct number of significant figures. And we'll look at that a little bit today. So that's going to be like a standing assignment from here on out. If you do any kind of mathematical calculation, make sure you're following either sig figs or decimal places, depending on what rule applies. Periodic table will be provided, hopefully to prevent you from having to scroll all the way back up to the top. I've put it in a couple of places throughout the test. So anyway, the entire test will load and open for you. It's not the situation where you have to answer a question before you can move forward. The entire test is open. If you get to a question where you're like, I'm not 100% sure, like skip it for that. Like don't do a time sink where you spend 20 minutes trying to figure out this question and then you run out of time at the end. Just skip it, go on, answer the questions that you know quickly and surely, and then go back to that at the end if you have time. It is a combination of multiple choice and short answer questions. Short answer, like we saw in chapter 3 credit quiz, where you have to enter in the setups, like what goes in the numerator, the denominator. So I have to grade those, obviously. And then there are other like written response questions that I will also have to grade. So when you're done, it's just going to show you that it's submitted, but it will not give you a score. I've got to go in and grade it myself. So I'm going to do my best to get these all done on Friday. So I'll send an email out as soon as they're all graded. So from chapter 1, a lot of conceptual information here. So we talked about element, compound, mixture. You saw this on the first credit quiz. Elements and compounds, those are pure substances. And that means that they have a constant composition, whereas homogeneous and heterogeneous mixtures are obviously a mixture of substances, and those mixtures are not definite. So it's not like every time you make a saltwater solution, it's the exact same amount of salt and the exact same amount of water. There's variability. So mixtures are not pure. They have variable composition. Homogeneous is when, of course, they look the same throughout. You can't tell that there's different substances. Example there would be like milk, right? You can't see the calcium, the protein, the water, right? It looks the same throughout. Heterogeneous, like oil and water. You can definitely tell it's not very well mixed. You can see the separation. Be able to identify a chemical versus a physical change or property. So if I said something like aluminum is a silver shiny solid at room temperature, those are physical characteristics. We're not doing anything to the aluminum. We're just describing what it looks like, smells like, whatever, without doing anything to it. right? A chemical property is when we describe what I always thought of was like the chemistry of it, right? So we're going to take that aluminum foil, maybe like we did today in lab, except it's an aluminum wire, and we put it into a copper 2 sulfate solution, and all of a sudden the wire turns an orange brown color, right? Copper color. That is describing, kind of in my mind, the chemistry, right? We're taking that aluminum and we're adding matter to it, and then we're explaining what happens, and that's a chemical property. A physical change, I always just kind of thought of that as a phase change, right? That's the easiest, right? Where we take like melt ice or boil water, right? The composition of the matter doesn't change. We've just changed the appearance. Look over in the notes from chapter 1, the 5 parts of the scientific method. Just make sure you have that at the ready in case there's one question about that. Exothermic, a lot of you answered this very well in the first quiz, right? That's when heat exits the reaction. Endothermic is when the heat or energy flows into the reaction, it's sucked into the reaction. Kinetic energy, energy of movement, and then potential energy, energy of position, right? Stored energy. Now, there were 6 prefixes in the chapter 1 notes. All right. So I'm going to just pull out my chapter 1 notes here really quick. Because sometimes students will be like, well, I didn't realize I had to memorize that. So I just want to make sure that I'm being clear. So when you look at the chapter 1 notes, right, a lot of the definitions that we've gone over so far, they're all here for you. Let me go to, there's the 5 parts of the scientific method on page 2 of the chapter 1 notes that you can look over. But then when we get down to page 4 of the chapter 1 notes, right, it says, okay, we need to memorize these 6 prefixes. So mega, kilo, centi, milli, micro, and nano. So review those if you need to. And then there were also 4 conversion factors that I wanted you to memorize. And that is on the second to the last page. Yeah, second to the last page of the notes where you get to the dimensional analysis section. Again, memorize. We have an inch is 2.54 centimeters. 1 kilogram is 2.205 pounds. Or if you remember that a pound is 454 grams or 0.454 kilograms, that's fine. You just need to have a conversion memorized between the metric system and of course pounds. And then 3.785 liters in a gallon, and the cubic centimeter and the milliliter are equivalent. It's a 1-to-1 ratio. Any other conversion factor you need, like if it has pints or quarts or tons or feet, I'll give you anything else. But these 4 conversions, I want to make sure that you have memorized. All right. Let's see. Precision versus accuracy. Y'all did well with this, right? Precision is repeatability. So if I do the same test over and over and over again, or calculation, I get the same result. That's good precision. Accuracy, though, is how close you get to the actual value. And so they don't necessarily go together. Sometimes you can have good precision and poor accuracy, and sometimes you can have good accuracy and poor precision. The other thing I want to make sure I don't skip over here. We talked about the prefixes, the temperature conversions as well, Fahrenheit to Celsius, and the 4 conversion factors. Okay, so the temperature conversions, we've got, if you have Celsius, you want to add 273.15 to go to Kelvin. An intro, I think the online class just had it as 273. We can go ahead and give the 0.15 a little more precision here. Now, since we're adding, if whatever the temperature is that's given to us in Celsius, that temperature's decimal place is what matters. So if I give you a Celsius temperature of like 25 degrees Celsius, when I convert it to Kelvin, it's going to go to 298. It'll keep the ones place. But if I say it's 25.0, then I need to go 298.2, right? So then I'll keep it to the tens place. So whatever temperature you're given, the decimal place of that is what tells you the decimal place of the answer. So it follows the decimal place rule, not the sig fig rule. And as I was looking over the quizzes for that chapter, I did notice that there were more than a handful that maybe got most of the credit, but a partial deduction just because you didn't have the correct decimal place. So definitely review your credit quizzes, right? And make sure anything that you're not sure why you had points taken off, you can look at the feedback box, open that up, see what it says. And if you still have any questions for me, please let me know. And I want to make sure you understand it before the test comes. Fahrenheit, if you have Celsius, multiply by 1.8, then add 32. And the same thing, look at your decimal place of the Celsius temperature. That'll tell you where to go for the Fahrenheit temperature. In the opposite order, right? Fahrenheit minus 32, make sure you hit enter and then divide that by 1.8, and that'll get you to Celsius. All right. And then the last thing here was density. Density we know is mass over volume. So be able to solve for density. If I give you the mass of an object and the volume, and you may have to get volume by displacement of water, right? So you have to do it by subtraction. Or if it's length times width times height, make sure if I give you those 3 dimensions, you multiply them together, that'll get you your volume. If you're dealing with a liquid, you're probably going to have to get the mass of the liquid by difference. It'll say, okay, here's the mass of the empty cylinder. Now here's the mass of the cylinder with the liquid in it. Subtract those two, that'll tell you the mass of just the liquid. All right, so that's chapter 1. Definitely look back over those practice quizzes. The practice quizzes stay open the entire semester, and always the highest grade sticks. So if you already took it and you got a 1 out of 1 on practice quiz 1A, you're like, well, I don't want to take it over again because I don't want to lose my perfect score. You won't. So just take those again if you want, even just to open them back up again, just to see what they look like. You can do that. The credit quizzes you can't take again, but you can certainly review your submission, and then let me know what questions you have. Then chapters 2 and 3, I kind of broke this up from TRO just because I didn't like the way it was organized in the book, but atomic structure, subatomic particles, protons, neutrons, and an electron. Make sure you're okay with doing that for either an atom or an ion. And we're going to look at that here in just a second. Isoelectronic, that happens when you have either atoms or ions with the same number of electrons. So they have the same electron structure. Know your family names like transition metals, alkali metals, halogens. Be able to determine the weighted average for the atomic mass of given isotopes of an element. So there was an example in the chapter 2 notes that we looked at where we were trying to find, I want to say it was bromine. Let me go find it really quick. Oh, it was copper. I'm sorry. And we wanted to find that mass number on the periodic table for copper. We were explaining, why is it not a whole number? And it's because there are different isotopes of copper, and the weighted average of those isotopes is how we end up with that mass number. And so the example is, okay, I've got these 2 isotopes. The first one has an atomic mass of 62.9291, and that makes up about 69% of your sample of copper. Then the other isotope of copper has a different atomic mass because it has more neutrons in it, and it makes up about 31% of the sample. So the way you do a weighted average is you take that atomic mass that's given times the percent abundance, just changing it to decimal form, and then you add that to the product of that second isotope mass times the percent abundance converted to decimal form. Then when you add those two together, that's how you get your weighted average. So be prepared for something like that. All right, so that's how you do the weighted average. That's in the chapter 2 notes. The nomenclature, definitely going to be some questions on that. We're going to review that a little bit. So, since it's mostly multiple choice with the nomenclature, definitely know the little tricks. When do you use hydro for an acid? When do you have an IDE ending versus eights or ites? When do you use prefixes? When do I need a Roman numeral? That's all going to be super important. Also, make sure here that you have memorized your polyatomic ions. I know for me, that was the hard part. I think I've mentioned I don't love memorizing things, but the polyatomic ions need to be memorized, and your element names and symbols. Not all of them, obviously, just the ones on the periodic table where you don't have the name provided. So we had talked about that. This is a good way to quiz yourself. You can print out one of these periodic tables, and if the name is not there, that means you should know what it is. If the name is there, that means don't worry about it, right? Because this is the table you're going to get. So if I talk about chromium, I need you to know that that's Cr. Okay. If we're given the percent composition, we want to be able to find the empirical or molecular formula. I guess a couple of handfuls of quizzes I've done, I've graded for chapter 3. It looks like most people did great with empirical and molecular formula, also with percent composition. The molar mass of the compound, I think that was like the first 3 questions on the chapter 3 credit quiz. Invariably, or like always, there's just going to be subtle differences in your molar mass and another molar mass, right? Like, don't worry about that. So if I had a molar mass calculation where I got 249.72, and when you did it, you got 249.71, don't worry about that. But I'm going to fix all that. So it's close enough. If it's more than like 0.2 off, then I think maybe something went wrong. Let's see, Avogadro's number, right? So make sure you have that memorized. Avogadro's number, 1 mole is 6.022 times 10 to the 23rd. And the particle type depends. This was the last quiz on the chapter 3, last question, sorry, on the chapter 3 credit quiz. So if you have an element like sodium, your particle type is an atom. If it's a compound like water, then your particle type is a molecule. So just make sure that you evaluate that. Like if you're given the mass of a compound, then we're going to go to moles using molar mass of that compound, and then we would go to molecules using Avogadro's number. Because it's a compound, right? We go to molecules. Your 7 diatomic elements, this really shows up in chapter 4, but it is in the chapter 3 notes or 2 notes. These are your 7 diatomics: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. And so when we see these in equation writing, we know that if we're talking about oxygen gas, we put O2. All right, we're going to review that here a little bit. All right, then chapter 4, speaking of chemical equations, if I give you reactants and products, then just be able to balance. So that's following the law of conservation of mass. If we have a balanced equation, then we can do some stoichiometry. And of course, your pass-through is always going through the multimole ratio that's comparing whatever 2 substances you're looking at. Then on top of stoichiometry, we can look at percent yield. Because we're not in lab, the actual yield will be given. And as we talked about, the actual yield will always be for a product, which means the percent yield will always be for a product. And let's see, question was, are particles interchangeable between elements and compounds? It's not interchangeable. The particle type is just different. If it's an element like sodium, the particle is called an atom. If it's a compound like water, the particle type is a molecule. It's just a language thing. So atom means singular, like Fe. Molecule means it's going to be plural, like H2O or CO2, something like that. So it's just a different name, but it's the same idea. Limiting reactant. Also, what's new, we haven't done this since we didn't do this in intro. We looked at limiting reactant, but we didn't talk about excess reactant. So we did that in the chapter 4 notes. Combustion reactions, we're going to look at those. That's where you always make CO2 and H2O gas. And then the reactions of the alkali metals with a halogen like chlorine or water. There was also oxygen in there too, but those are the equations we're going to look at. So first thing I did here is I wanted to review nomenclature, only because for me that was the hardest part. So N2O5, remember what we talked about was when you go to do nomenclature, always identify what the first element is. Is it metal, non-metal, or hydrogen? So I can see nitrogen over here to the right of my stair step, which means it is a non-metal. And what that means is this is a covalent compound, and that means I'm going to use prefixes. All right, so what I need to do here is just say, okay, how do I say 2 nitrogens? Well, I'm going to say di-nitrogen. Remember, the first element you name as is and use a prefix if there's more than one. And then I need to say there's 5 oxygens. So I'm going to say penta. And then with the second nonmetal, you always push that IDE ending. So di-nitrogen, pentaoxide, or pentoxide. So 2 nitrogens with 5 oxygens, binary compound IDE ending. All right, next one we've got is K2SO4. So again, first thing I do is I look at K. All right, potassium is a alkali metal, right, family name. So with metals, you have to ask yourself, do I need the Roman numeral? And the idea is that if you know the charge based on position, that means we don't need the Roman numeral. Potassium is a group 1 alkali metal. It is always a +1. So that means I don't need the Roman numeral because it's not in doubt, right? So I'm just going to say K is potassium. And then that's all I have to do for that cation. Then the second part of this is a polyatomic, right? It's always just two pieces. Even if it looks like more, it is just two. So we've got the cation, the potassium. Now we have to know what is SO4, and this is where the memorizing comes in. So I had mentioned in the video, when you're learning your polyatomic ions, try to focus on all the eights especially. So you're going to remember that SO4 is called sulfate, because then what you'll remember is SO3, one less oxygen, is called sulfite, right? Less oxygen gets the ite ending. So definitely review your polyatomic ions, but 8 ending because polyatomic, SO4, sulfate. When I look at the next one, I've got Cu2S. Now copper here is another metal. So here's what we got to think about again is, do we need the Roman numeral? And copper is a transition metal that we don't know the charge. Remember, aluminum is always a 3, zinc is always a 2, silver is always a 1. Copper, we don't know. It can have 2 or more possible charges. And so that means here we're going to need the Roman numeral. So I'm just going to abbreviate that RN. So the only way to know copper is to know sulfur. So I'm going to start with the sulfur. When I look at my periodic table, my charges start at 0 for the noble gas family. They have what everybody's looking for. They don't typically ionize, so we're going to leave that as a 0. Your halogens, -1. Oxygen family, including sulfur, is a -2. Nitrogen, -3. So sulfur should carry a -2 charge. Now you can do the reverse crisscross. So if you like the reverse crisscross, when you have your compound, Cu2S, if the charge on the nonmetal is the subscript on the metal, absolute value, right? So the charge of sulfur is 2, the subscript on copper is 2. Then that means the opposite will also be true, meaning the subscript on sulfur, not there, so it's technically a 1. That would be the charge on the copper. All right, so it's a crisscross. Alternatively, the way you could figure it out is, okay, you know, sulfur is -2. And you know that you have 2 coppers because it has a subscript of 2. So to get these to balance out, I've got -2 from the sulfur. I need a +2 from the copper. So that means each one must be a +1 charge. So when you name it, you want the charge on each copper. So this would be copper 1, and then an IDE ending this time because, again, it's binary. So only 2 elements, IDE ending, only 2 elements, IDE ending. So that's true with both covalent and ionic compounds, that we push the IDE ending whenever it's binary, right? Only 2 elements present in the compound, we always make that IDE ending. Now, with acids, it would make sense. We would just do an IDE ending. But no, they decided, okay, here's what we're going to do with acids. Number 1, we're going to call them acids by saying acids. Okay, so that's helpful. Number 2, the big thing with acids is to remember when to use hydro. So because HBr is just hydrogen and a nonmetal, meaning it is a binary acid, that's when we use hydro. If hydrogen is with a polyatomic, then we don't use hydro. All right, so this is what you have to make sure to remember to connect, that if hydrogen is just with a simple nonmetal, no polyatomic ion, that's when we start with hydro. So HBr is called hydrobromic acid. So all we had to do here was plug in the stem for bromine, which is the BROM. All right, so hydrobromic acid for HBr. All right, now if we're going in the opposite direction, you know, it's some students like the naming better, some students like the formula better. So I don't know if I can say which one's easier or harder. So this one, zinc perchlorate. So zinc we know is Zn. There's no Roman numeral here, so that means we should know the charge. And I should back up before that and say we know this is ionic because zinc is a metal. And if there's a metal in front, then we know we have an ionic compound. And what's important with an ionic compound is we have to balance the charges. So we have to know our charges and we have to make them balance out. So zinc, like we talked about, remember your 3, 2, 1. Zinc is always a 2 plus 2. And then we've got perchlorate. So that definitely doesn't sound just like an element, but it's also missing the IDE ending. So definitely pay close attention to the last 3 letters. If it's an 8 or an ite, exception of course is cyanide and hydroxide. But otherwise, if it's an 8 or an ite, it's going to be a polyatomic ion. All right, so the 8 ending here tells me I have a polyatomic ion. This is just going to come from memorizing. But remember, chlorate is ClO3, -1. Perchlorate is the most oxygen, which is ClO4, -1. So remember, in an ionic compound, that's your job, is to name the ions. So when we say zinc, we know Zn plus 2. Perchlorate, we know, is that polyatomic ion, ClO4, -1. Now, charges have to balance. So because zinc is a 2, I would have to have 2 of the perchlorates to get a -2 so that my charges can cancel out. So my formula here will be 1 zinc and then ClO4 subscript of 2. All right, iron 2 nitride. The Roman numeral here tells me that this is an ionic compound. So again, I have to balance charges. So just don't forget, when it says iron 2, that 2 gives you the charge on the metal. So I know iron 2 means Fe plus 2. The other thing I always focus on with ionic compounds, last 3 letters. IDE is telling me that this is just a non-metal. It's not a polyatomic. So we're just looking at nitrogen, and that charge on nitrogen is a -3. So again, those 2 charges don't balance. So you can either think, okay, least common multiple of a 6, or do the crisscross. So the charge on the iron would become the subscript for the nitrogen, and the charge on the nitrogen would become the subscript for the iron. So when we're done, we would have Fe3N2. All right, so that would be iron 2 nitride. Next one, we got 2 acids to finish up. I've got sulfurous acid and phosphoric acid. And the acid means I have H as my cation. In both of these acids, we're not seeing hydro. So again, kind of going back up here, right? It's only when it's hydrogen in a nonmetal that we make sure we put hydro in front. This is saying, okay, there's no hydro in front here. So that means we have hydrogen with a polyatomic instead this time. And that's also true in the phosphoric acid. Now, what is the polyatomic? So there's an ending change, right? Us, again, the last 3 letters. The us came from ite. So we're looking for sulfite. All right, so sulfurous comes from sulfite, polyatomic ion. So up above, when we looked at sulfate, we knew sulfate was SO4, so sulfite is SO3. All right, and the charge on that one, -2, like we expect, because sulfur's -2. So in sulfate and sulfite, it's nice, it keeps the -2. So balancing here, -2, we'd have to have 2 hydrogens to get a +2 to balance. So our formula here would be H2SO3. So that would be sulfurous acid. Phosphoric acid, different last letters here. Ich would have come from 8. So we want to know what is phosphate. Instead of phosphite, we want phosphate this time. So you just remember, us came from ite, ich came from 8. So phosphate, polyatomic ion, is PO4 -3. So -3 needs a +3 to cancel out. I'd have to have 3 hydrogens to balance. Formula here, H3PO4. All right, and now most of the time with the polyatomics, they literally drop the 8 and replace it with us, or they drop 8 and replace it with ic when they name the acid. But only in these two, the sulfur and the phosphorus, do they bring in that extra syllable. So instead of sulfus acid, it's sulfurous. Instead of phosphic, it's phosphoric. But sulfur and phosphorus are the only two that do that. All right. So that's nomenclature. We reviewed a little bit of everything. If it were me, I would be definitely studying my polyatomic ions, and I would probably be going back over nomenclature videos just to make sure I got it. Practice quizzes again. If you want to just open it and try a few of them, submit it, knowing it's not going to be a good score, that's okay. It's just for practice. All right, then this next question, we've got Fe3BO3. And I just want to go ahead and again, review the nomenclature while we're here. Fe3BO3. BO3 is a polyatomic ion called borate. Borate BO3 is a -3 charge. So you have to be a little careful with this one because it's not BRO3. BRO3 is bromate, but BO3, that's boron. So it's borate. It's a -3 charge. You have 3 irons to balance. So that means each one must be a +1 charge. So the name on this would be iron 1 borate. All right, but again, I'm just putting that in there just to practice nomenclature one more time. If we're looking for the percent composition, right? Percent means we got to do some math. There's no numbers here. So what we do is we first find the molar mass of that compound. So I have iron, I have boron, and I have oxygen in my compound. I have 3 irons, only 1 boron, and then 3 oxygens. Atomic mass for iron, I would do 55.85. Like we talked about, I like going 2 decimal places. If you want to keep it as 0.845, totally fine. Just don't round it to 0.8. At least go 2 decimal places for me. All right, boron while we're here, 10.81, and then oxygen 16.00. All right, then oxygen I have to take times 3. So I really have 48 grams for all 3 oxygens. Oops. Boron, there's only 1. For the iron, we have to have 3 as well because of the subscript of 3. So on my calculator, I'm going to take that 55.85 and multiply that by 3. And I get 167.55. Boron stays 10.81. And then the 3 oxygens is 48. So when I add all of that together, I get 226.36 grams. All right, that's the total mass of the compound. So mass percent, what I'm going to do is figure out, okay, in that, what percentage of the mass is due to iron? What percentage is boron? What percentage is oxygen? So percentage of iron, total mass of iron, 167.55, divided by the total mass of the compound. And then times 100. So 167.55 divided by 226.36 times 100. Again, there's not really any sig figs here to follow, but I go 2 decimal places just like I do with molar mass. So it's about 74% iron. For the boron, 10.81 grams divided by the 226.36 times 100. And what I get here is 4.78%. And then oxygen, last one, 48 grams for all 3 oxygens divided by the 226.36 times 100. And here I get 21.21%. All right, at the end, I just like to add up all my percentages just to make sure that it looks good, like I didn't add something up wrong. It should get me to 100%. I got, basically 100.01, but that's just rounding, that's okay. So percent composition, typically pretty straightforward. All right, now the next review question we have, what I was mentioning is for the first part of chapter 4, the first item, it says, okay, if I give you reactants and products, let's just be able to balance that using the law of conservation of mass. This isn't any special type of reaction that we've learned, right? It's not well, we haven't done doubles yet, sorry. It's not combustion, it's not reaction of alkali metals. So there's not a perfect place to start. But I will say if there's an element that goes and splits into two places, you do that one last. So chlorine, for example, is just in the hydrochloric acid on the reactant side, but on the product side, it's in two different products. So do chlorine last. So if I just start with manganese, manganese looks good. Both sides, there's only one manganese, so we're going to now go to oxygen. In the MnO2, which would be manganese 4 oxide, there are 2 oxygens present. So on the product side, all that oxygen came out in water, but there's only 1 oxygen in the water. So I would have to make 2 waters to get 2 oxygens to balance the 2 oxygens on the reactant side. Now, when I did that, that 2 in front gave me a total of 4 hydrogens in the water molecules. So in front of the HCl on the reactant side, because I only have 1 hydrogen, I should multiply that by 4. When I do that, that gives me 4 chlorines. So now let's check. I've got 2 in the MnCl2 and another 2 in the diatomic chlorine. So there's my 4 chlorines to balance. So now my equation is balanced. So question says, what is the percent yield, now that we have the balanced equation, if 100 grams of manganese 4 oxide produces 45 grams of chlorine gas? So according to my question, I have 100 grams of the manganese 4 oxide, and it says I produce 45 grams of the chlorine gas, the Cl2. We're looking for percent yield. And so your formula for that is you need the actual yield over the theoretical times 100. And when you look at this, the chlorine, the Cl2, is the product. So we are going to be finding the percent yield of the Cl2. And so that means that 45 grams of Cl2 is the actual yield. So then I need to know what is the theoretical yield of Cl2 before I can figure out the percent yield of the reaction. So that means that the chlorine is my B. It's where I'm headed. Like I got 45 grams, but how much was I supposed to get? And that 100 grams of MnO2 is my starting point. So what we talked about was whenever you have mass given or asked for in a stoichiometric calculation, the only way that you can do that calculation is going through the mole, right? And the only way to get from mass to moles or moles to mass is through molar mass. So we have to have the molar mass of the MnO2. So if I go to my periodic table, manganese is 54.94. 2 oxygens would be 16 plus 16 to be 32. So my molar mass of MnO2 is 86.94. And then for the chlorine, it is 35.45 taken twice. So that would be 70.90. So we have to have those before we can really do any calculations. So I start with my measurement, not the constants, right? The periodic table, those are constants. We don't start with our constants. We start with the measurement that's given to us in the question. So I have 100 grams of MnO2 going to moles first. If in doubt, always go to moles first. It is the center point of all of our chemistry calculations. The molar mass from the periodic table, 86.94. That goes on the bottom. Sorry, that was supposed to be okay. MnO2. There we go. Middle step is always the mole to mole ratio. So we got rid of grams of MnO2, we got to moles. Now we can get rid of moles of MnO2 on the bottom and go to moles of the Cl2 on top. And that's going to come from the balanced equation. So for the MnO2 balanced, we just, nothing in front, so that means it's a 1. And the chlorine also just a 1. Now, if this was a problem why I'm asking you to show your work, even if it is a 1-to-1 ratio, you might think, well, mathematically, I'll just leave it out because it doesn't matter. I still want you to put it in. And it's because I need to know that you know that that mole ratio goes there. So even if these numbers cancel out, I still want you to put them in. Okay. And then 1 mole of Cl2 on the bottom to go away is 70.90 grams. All right. And like we talked about with molar masses, if you're doing a molar mass, the subscripts matter. So 2 chlorines, total 70.90. The coefficient in front, however, does not affect the molar mass. So molar mass of HCl is just about 36 grams. The 4 in front is saved for the mole ratio step. All right. So when I do these calculations, as we talked about, they're based on everything being perfect. So things are not always perfect, as we know. So this is a theoretical yield. In theory, if everything's good, this is what we should get. All right, so I'm getting ahead of myself. It's 81.6 grams of Cl2, and that is my theoretical yield. Okay, my brain and my hand have been a little off in sequence, in speed all day. So I was thinking about, okay, I'm getting my percentage next, but anyway, not yet. So this is my mass. So in theory, if everything's good, this is the mass of Cl2 we should get. All right. Now that assumes that we have unlimited HCl. And since it's not mentioned in this question, that assumption works, right? We're going to see questions where that's not the case here in a little bit. All right. We got 45 grams. We should have gotten about 82 grams. So not great, but our percent yield would be the actual 45 grams of Cl2 divided by, just one sec. Yep, the theoretical of 81.6 grams of Cl2 times 100. All right, so let me pop out the answer here really quick, and then I'm going to answer the chat question, which is a really good question. So I got 55% as my percent yield of the Cl2. So a question came in about the zeros, and the zeros, that is the only tricky digit when it comes to sig figs. The 100 here that we were given, we have 3 significant figures. The zeros, when they are after the last non-zero digit, so 1 is the only non-zero digit we have here. When the zeros fall after the last non-zero digit, they are significant as long as there's a decimal written in. So because that decimal was there, it's emphasizing that those zeros are significant. So 100 dot has 3 significant figures. So when we do our calculation, our theoretical yield needs to also have 3 significant figures. When I came to the next step to do the percent yield, my actual yield that was given to me in the question of the chlorine, this is only 2 sig figs. So that means when I do the percent yield, I can only do 2 sig figs. So always least wins. In the first one, though, the stoichiometry, we started with 3 sig figs. Don't look at the constants. We're going to end with 3 sig figs. When I now go to do percent yield, I have a 2 sig fig number divided by 3 sig figs. So my answer can only have 2. So I had to stop it just at 55%. I didn't just arbitrarily decide to round it to a whole number. I followed the sig figs of the least, which is the actual yield at only 2 sig figs. Now zeros, the other time zeros come into into play and maybe make things a little more complicated is if you have zeros in front. So I'm just going to grab my sheet of paper here really quick, the one I just used. So if I had 0.026 grams, that would only have 2 significant figures. So the leading zeros, the zeros that come before the first non-zero digit, these are just called placeholders. They're for magnitude only. So there's only 2 significant figures here. If you had 26.0, then you have 3 sig figs, right? Because the 0 is after the last non-zero digit and there's a decimal written in, so 3 sig figs. If I have 260, no decimal written in, now I'm looking at only 2 significant figures. Now the question was back up here, 55%. What if I wrote it as 55 with a decimal and then percent? And the answer is it doesn't help you and it doesn't hurt you. So either way, you've got 2 sig figs. The only time the decimal is really important is if there's a 0, like at the very end. Like, for example, if I had done this calculation of 45 divided by 81.6 and my calculator gave me 50, but I need to say, this is 50 with 2 sig figs, then I have to make sure that I put the decimal in. But if I only want it to be 1 sig fig, then I would just leave it as 50 with no decimal. And that would tell me that 0 is just a magnitude 0. So just 50, no dot, %. So with the 55, that the 2 5s are significant either way. So the decimal doesn't help and it doesn't hurt. So that means you can put it on or you can leave it off. It's going to be 2 sig figs either way. All right. So that's a little bit of stoichiometry, passing through mole ratio, always in the center. Remember, if you're going to be asked for a % yield, 2 things. Number 1, it's always going to be for the product. So when you see MnO2, you're like, reactant, I'm not looking for the % yield of that. And then you got the chlorine, which is a product. So you're like, okay, I'm definitely looking for the % yield of that. That's going to be what I need to look at. That also means that the actual yield of that needs to be given. So when it tells me this 45 grams of Cl2, I know then that that is my actual yield that I'm going to save for my % yield calculation. All right. All right. Next question, unit conversions. What would be the mass of mercury in pounds? Mercury from hydrogyrum, which means liquid silver, Hg, right? In pounds, and we have a 5.0 gallon container. So reviewing some of our conversions, we have 5.0 gallons. Sorry, the decimal kind of got squeezed. So first conversion, you had 4 to memorize. This was one of them. 1 gallon is 3.785 liters. All right. Then what I notice is I have a volume in liters. My density, which is going to help me get from volume to mass, that unit is in milliliters. So I'm going to do another conversion here. This time it's just a prefix, and it's the milli prefix. So again, you've got options. If you want to do it the neutral way, you're going to put 1 with milli and 10 to the negative 3 liters on the bottom, because the way that the usual Gen Chem books do it is you put 1 wherever the prefix is, and then you sub the prefix with the exponent. So 1 milliliter is 10 to the negative 3 liters, and that works totally fine. The other way you do it is the way we did it in intro, which is 1,000 milliliters in a liter. And it's the exact same. It gets you to the same place. So you do whichever one you like better. Now, once we have milliliters, density is going to take us to grams. All right, so that density, remember that slash is an equivalence line. So 13.6 grams is equal to 1 milliliter. We put milliliters on the bottom to cancel out, grams on top. Last thing is we want to convert now to pounds. So a couple of options here. If you remember the 454, you can go right from grams to pounds, but I'm going to do the 2 conversions that are on your list to memorize. First thing is to go grams to kilograms. So as I was mentioning, the new Gen Chem way is wherever the prefix is, you put a 1 and then you sub the prefix with the exponent. And kilo is 10 to the 3rd, but 10 times 10 times 10 is 1,000. So that looks like it did in intro. 1 kilogram is 1,000 grams, right? Then from there, we're going to get rid of kilograms on the bottom and go to pounds. And I have to say, like this one, I think I overthought it. So then I just remembered to be like, okay, pounds is the bigger number. So pounds, 2.205, kilogram, only 1, right? And that helped it stick for me. So dimensional analysis, units are canceling out as you go. Top and bottom, numerator, denominator. And then basically on the calculator, we just start multiplying and dividing. I tend to go step by step by step. That way I'm less likely to miss something. Some students like to multiply everything on top first, then go back and divide. That's fine. But I go step by step because again, I'm likely to just overlook something. So 5.0 times 3.785 times 1,000 times 13.6, and then divide it by 1,000, or 1 times 10 to the 3rd, and then multiply by 2.205. All right, so I'm going to type it in one more time. So 5.0 times 3.785 All right, then times 1,000 times 13.6 divided by 1,000, and then multiply by 2.205. Calculator gives me 567.5229. And then, of course, we got to think about significant figures. So 5 gallons, 5.0 is 2 sig figs. Your density here is 3 sig figs. Least always wins, so we want 2 sig figs for the answer. So when I think about how to round this, what I'm going to do is think about my 5 and 6 being my 2 sig figs. What I'm cutting off, though, the 7, means the previous digit needs to round up. So that 6 is going to become a 7. And then I need a 0 just to show where that decimal is, right? It's a placeholder, so it's a magnitude 0. Now, I don't want to put the decimal on it because then that's a 3 sig fig value, and I just want 2. So in that case, the decimal would be wrong. We just want 570 and then pounds. That would be my answer for that volume of mercury. All right. Next question here. We've got temperature. We're going Fahrenheit to Kelvin. The only way you can do this is you have to pass through Celsius. We don't have a direct Fahrenheit to Kelvin, so we got to go to Celsius first. So we're going to take 22.3 minus the 32 first. Remember to hit enter and then divide by 1.8. So 22.3 minus 32, and then divide that by 1.8. And calculator gives me negative 5.3, basically 8 repeating. We're going to keep the same decimal place as the original temperature. So I'm going to round this. I'm going to stick to the 3. What I'm cutting off is 5 or greater. So this is going to be negative 5.4 Celsius. All right, so negative 5.4 Celsius. And then I'm going to add 273.15 to go to Kelvin. All right, and then what I'll do is I'm going to, again, go to the first decimal place. So this is going to go 267.8. All right, so that would be my temperature from Fahrenheit to Kelvin. So make sure you have your formulas memorized. If you had kept this as 5.3888888 and then added that, your last digit here might have been slightly different, and that's okay. As long as you keep the same decimal place. No, it still would have been an 8. Never mind. It would have rounded to the same 0.8. All right. But remember, the rule with temperature is focus on the decimal place. Okay, so look, our sig figs are changing. We have 3 sig figs in Fahrenheit, only 2 in Celsius, and then 4 in Kelvin. But it's not the sig fig rule, it's the decimal place rule. So that's what we're focusing on always with temperature, is how far past the decimal should we go. All right, so temperature conversions. Then next one, we're looking at isotopes, subatomic particles. So we have 26 protons, 30 neutrons, 24 electrons. So the one that is always revealing, it always tells you what the element is the atomic number. So 26 protons, number of protons, that is your atomic number from the periodic table. So when I go and I look for element number 26, I see iron. So I know right here 26 protons means I have iron. Now, the mass number is the number of protons and neutrons added together. So 26 plus 30 gives me 56 for my mass number. So what I know here is with my iron, I'm looking at iron with a mass number of 56. But if we do that isotope notation, which is kind of new for Chem 1, we would have our mass number of 56 and our atomic number of 26. Now, the last thing is here, we've got 24 electrons. So what I notice is my proton and electron count is not equal. So that tells me that this is an ion rather than an atom. So what's the charge? Well, if I have 26 positive particles and 24 negative particles, I can see that overall I'm going to have a +2 charge. The other way you can look at it is you've lost 2 electrons. To go from the atom to the ion, we've lost 2 negative particles. So that means that this is carrying a +2 charge. So this would be our isotope in that new notation, right? We'd have mass number of 56 on the top, atomic number 26 on the bottom. There's our element symbol, iron. And then because it's an ion with a charge of +2, we indicate that to the top right. All right. Mass percent of carbon in sodium carbonate, decahydrate. So mass percent, this was another way we could do mass percent rather than just breaking down every element in the compound. Maybe we're just looking at one particular thing. So sodium, reviewing the nomenclature, group 1 alkali metal, +1 charge. Carbonate, 8 polyatomic, means it's a CO3 -2. Deca, meaning 10, hydrate, meaning water. So carbonate -2, sodium +1. To get the charges to balance out, we'd have to have 2 sodiums. So my formula here is Na2CO3 dot 10 H2O. All right, so there's my sodium carbonate decahydrate. And I want to know the mass percent of just the carbon. That's what we're going to look at. So first thing is I need the molar mass of the whole thing. Sodium, 22.99 times 2. Carbon, 12.01, but we only have one of those. Oxygen is 16.00. Now I've got 3 in the carbonate plus another 10. So I have a total of 13 oxygens. And hydrogen, which is 1.01, I've got 20 of those in those 10 water molecules. So I got to multiply that by 20. So I've got a total of 208 grams for the oxygen. And then I've got 20.20 grams for those 20 hydrogens. I've got 12.01 for the carbon. And then I've got the 22.99 times 2 for the sodium, which is 45.98. So all together, I have 268.19 grams. So if I just want to know the percent carbon, then I'm going to take the mass of the carbon divided by the total molar mass of the compound times 100 to get my percentage. And what I get here is it's only 4.48%. So there is a question, just to give you a heads up, there was a question in the chapter 1. No, was it chapter 1? It's in the chapter, I'm going to go find it actually, because I want to make sure. Just actually, let me put it this way. When you're looking at the chapter folders, if I did any extra videos over specific problems in the homework, definitely look at those. So there's one question about percent, well, it's a combustion reaction, and you are given, it's basically what we talked about when we did empirical and molecular formula. This would, it's definitely not chapter 1, it's chapter 3 or 4. And it's a if like, remember when we were talking about empirical formulas, like you have this machine, the GCMS, and it'll tell you that it's 20% carbon and 40% hydrogen. Basically, these problems go through and they figure out exactly how that's done. It's a very good question, and I did a video on it, so just make sure you watch it. Okay, so we got a butane reaction, C4H10. Mass percent, yeah, so if there's no numbers given, and we're just using molar mass values, then I always go 2 decimal places, just like I do molar mass values. If there were mass measurements given that we were using for the percentages, then you'd go with sig figs. But because we don't have measurements, these are all constants, I go 2 decimal places when using the periodic table. All right, so we've got the combustion reaction of butane. So let's do that first. We got C4H10, and always the fuel for fire is the oxygen gas, right? Can't have anything really happen here unless we've got oxygen. The carbon all comes out as CO2, and all the hydrogen comes out as H2O. The balancing here, remember, like we talked about, we're going to save oxygen for last because it splits. So all of the carbon comes out as CO2. 4 carbons in the butane means we need 4 carbons in the CO2. So there's only 1 in CO2 times 4. With the hydrogen, we've got 10 total. On the product side, we need 10 to balance. We need the multiple of 2 that will get us to 10. So that means we're going to put a 5 in front of H2O. When I balance out the oxygen now, I've got 8 in the carbon dioxide plus another 5 in the water. So that would mean 13. So in front of oxygen, I'm going to put 13 over 2, or you could put 6.5. So question says we've got half a kilogram, 0.500 kilograms of butane. It's burned in 2.00 kilograms of oxygen. And we want to know the mass of the CO2 that we would make. So this is classic limiting reactant, right? I'm given quantities of both of my reactants. I'm looking for the mass of the product. So instead of doing one calculation, right, we get to do 2. All right, so I'm going to start with my molar masses, right? All of these are mass values, so we have to know molar masses. For the butane, I've got 4 carbons at 12.01 apiece, and then another 10 hydrogens at 1.01 apiece. So my molar mass here is 58.14. Oxygen, 16 times 2 is 32. And then for the CO2, 12.01 plus 32 is 44.01, right? So those are the molar masses from the periodic table. So I'm going to start with my butane and go to CO2, right? How much carbon dioxide could the butane make? I have 0.500 kilograms. 1 mole of C4H10 is 58.14 grams. Again, that was just from the periodic table. Mole ratio, for every 1 mole of C4H10, I'm going to make 4 moles of CO2. All right, that's when we bring in the coefficient in front. And then molar mass is always based on just 1 mole. So 44.0 grams for 1 mole of CO2. So first calculation, 0.5, sorry, we're going to multiply that by 1,000 to get it into grams. So it's really 500 grams divided by 58.14. And then times 4 times 44.01. So I get here to 3 significant figures. Calculator gives me 1513.93, but I'm going to take 151, 3 sig figs, and then replace the 3 with the 0. So I get 1510 grams of CO2. Second calculation, now taking my A2 to B. I have 2.00 kilograms of the O2. That step that I omitted up here, just remember it's 1,000 grams in a kilogram, just real quick. Or you could multiply it up front and then just start with 500 grams and 2,000 grams, but just don't lose your sig figs when you do that. So 1 mole of O2 is 32 grams. Now we do the mole ratio, go into the same place, go into CO2 on the product side. And then on the bottom, if you want, again, you could do the 6.5, or you can leave it as 13 over 2. And then you've got 44.01 grams per mole of CO2. All right, so I've got 2,000 divided by 32 times 4 divided by 6.5, and then times 44.01. All right, so here again for 3 sig figs, I'm going to do 1690, so 1690 grams of CO2. So limiting reactant problem, what we figured out here was the butane, right? This is going to be the limiting reactant. It runs out first. And so that 1510, right, that is my max theoretical yield, right? Still theoretical because in theory, right, nothing's perfect. But in theory, if everything's perfect, that's what we should get. But remember, you always circle the smaller because, right, that tells you that the butane ran out first. Once you make that 1510 grams of CO2, the butane's gone. And so the reaction has to come to an end. So we figured out our limiting reactant. That means that the other reactant, the O2, is the excess. So we're not done yet. Question says, how much of the excess reactant would be left over? And we don't have that answer yet. So we're only going to end up making 1510 grams of CO2. The oxygen would have had enough to go to 1690, but the butane didn't. So we had to stop at 1510. So there's a couple of different ways you can do this. One way you can do this is you could use the 1510. You can start with that 1510 grams of CO2. Figure out what mass of O2 would have been used for that. And then take the 2000 grams minus the mass used, and that'll get you what's left. So just kind of throwing out some numbers. I take my 1510 grams of CO2. I go through all the stoichiometry and I figure out that I used, I don't know, 1700 grams of CO2. Well, I started with 2000. So that would have meant I had 300 grams left. All right. Alternatively, what you could do is you can look at the difference in these two values with the product. Oxygen had enough to give me 1690 grams of CO2, but only 1510 was made. So this is another way you could do it. You can say, okay, I could have made 1690 grams of CO2, but the butane made it stop when I got to 1510. So if I do that difference, what I end up with is 180 grams of CO2 that wasn't able to be made. Now what I can do is figure out how much of that oxygen is not used because I didn't make that 180 grams of CO2. Whichever way you go, you're going to get to the same place. All right, so 180 grams of CO2, 1 mole of CO2, 44.01 grams. Mole ratio on the product side, 4 moles of CO2. And then for the oxygen, we've got 13/2 for the coefficient. And then a molar mass of 32 grams. All right, I feel like this is more direct because this is going to just be the final answer. I don't have to do an additional subtraction step at the end, but you do whichever one you make it that makes more sense to you. Okay, hold on 1 second. So I'm going to take 180 divided by 44.01 times 13/2 divided by 4, and then times 32. And it would be about 210 grams of O2 left over. Right, so we had 2000 grams and we would have only used about 1800 of it. We'd have 210 grams left over. So there's a couple of ways you can do it. The other thing I've seen students do is they look at it as a percentage. So 1510 is what percentage of 1690? Then that would be the percentage of O2 that you've used. So that would be another way you might think that's more direct. So if I take 1510 and I divide it by 1690 times 100, I made only about 89% of what I could have, which means I only used about 89% of the O2. So that's the other thing you could do on the calculator. I can take the mass I actually made of the CO2, divide it by the mass I could have made using the excess reactant, and then take that number and multiply it by the starting point. And then that would tell you how much I used, right? And then if I subtract that from the 2000, whoops, I forgot to add that. Anyway, you get to the same answer. So 1510 divided by the 1690. That's the percentage I used, times the 2000 grams of O2 means I only used 1786 or 1787. Now, if I take the 2000 grams and minus that, then that would tell me how much was left over. And it's the same answer I got when I was doing this down here. I just rounded it to 2 sig figs because of the 180. Yeah, and you could do it that way too. So another question, there's like that's the good and the bad of this problem. The good part is there's lots of ways to get to the same answer. The bad news is there's lots of ways to get to the right answer because sometimes you can overthink it or just kind of get confused by it. So the other question was, could you go back up here and now that we know what the limiting reactant is, use that to figure out how much O2 we actually used and then subtract that from the 2000 and that's also going to work. So all of those scenarios will work. So that's the good and the bad. What you use, whatever way makes sense to you, but we need to end up with for this question, what mass of the excess reactant would be unused, right? How much of it would be left over? And so I mean, we just went through 4 different ways of finding that, but you have to figure out the limiting reactant first. That you have to do. All right. Let's see, what else do we have here? I think that's it. One other just thing I want to review really quickly were the reactions with the halogens, halogens, water, alkali metals. So just to make sure, because this is on the list for chapter 4, but if you have an alkali metal like potassium and you react it with a halogen, right? Fluorine, chlorine, bromine, iodine. Remember, these are going to be diatomic because they're part of Hofbrinkel. So if you have iodine, it's really I2. So when those two come together, the elements separately, they don't have any charge. So they're not ions. These are in their elemental form. And iodine being diatomic has to be I2, just like oxygen gas back up here has to be O2, right? So when the two come together and form a compound, now because it's metal and nonmetal, it's going to be an ionic compound. So I think about my charges. Now that they're together, potassium is a +1 ion, iodine is -1. So this is just going to be Ki to balance out those charges. Balancing, because there's 2 iodines here, I need to multiply the Ki by 2. And then because that means 2 potassiums, I need to multiply the potassium by 2 on the reactant side. My states here, the metal is a solid, the ionic compound is a solid. The halogen, it would tell you, but basically at room temperature, fluorine and chlorine are both gases. Bromine is a liquid, iodine is a solid. But if it were a word problem, it'll tell you. It would say solid potassium metal reacts with solid iodine to make potassium iodide solid. The other thing we can have here is the reaction with water. So if I have potassium reacting with water, this is technically a single displacement reaction. And if you think of this like HOH, it probably looks a little bit simpler because remember what we were doing? We were talking about with single displacement, these two will switch places. So the potassium goes with the hydroxide and that's +1, -1. So that's balanced. And the hydrogen comes out as the element, but it's going to be, again, diatomic because it's part of Hofbrinkel. So this has to be H2, diatomic, just like I2. Now, balancing here, it looks a little weird because potassium looks fine, oxygen looks fine, but then with hydrogen, I've got 2 + 1, 3 on the product side, but only 2 on the reactant side. So we're going to multiply the water by 2. And what that does is it's now increasing the oxygen to 2. So let me track that. Remember, hydrogen, you always want to track at the end because it splits. So the 2 in front of water means 2 oxygens. So on the product side with the hydroxide, I'm going to put a 2 in front of KOH to give me the 2 oxygens. Now that also means 2 Ks. So I put a 2 in front of the K on the reactant side. Now looking at hydrogen at the end, there's a total of 4 in the 2 waters. And on the product side, there's 2 in the hydroxide plus another 2. So there's my total of 4. So this was on the list for chapter 4 that you may have to do the alkali metal with a halogen, the alkali metal with water. The other one we did was an alkali metal with oxygen. All right. And again, oxygen has to be diatomic because it's part of Hofbrinkel. Just like the H2 had to be diatomic because it's part of Hofbrinkel. And again, separately, just like with the iodine, these do not carry a charge, but when they come together to form an ionic compound, now they have charges. So the metal and non-metal, right, means ionic, means I got to think about charges. crisscross here, this should be K2O. Looking at oxygen, there's 2 on the reactant side. On the product side, there's only 1. So I'm going to multiply by 2 in front of K2O. Then 2 times 2 means 4 potassiums. So in front of potassium, I'm going to put a 4. All right. So that I think is a pretty good review. Just really quick here, I'm going to show you what I was talking about with the extra. There's lots here to keep you busy till Thursday to help you practice. You probably have caught that. There is worksheets in the folder. There's the practice quizzes, right? There's lots of stuff here. If you go into the chapter 3 folder, there's a specific TRO homework problem that is that combustion analysis question that I was talking about and how you then can get empirical and molecular formula. And I just have to find it, make sure I'm giving you the right number. Yeah, okay, so let me show my screen here to you really quick. No, not Teams. I tell you, Teams like always pops up, whether I like it or not. So this is the one I wanted. There we go. So I'm in the chapter 2-3 folder. So when you scroll down quite a bit, there is some worksheets here for chapter 3 to, again, more practice. Doing moles, percent composition, empirical molecular formula. Remember, you can do the worksheets and then check the answer key to see how you did. And then some Zoom sessions, but this is the one that I'm looking at. It says finding an empirical formula from combustion analysis. It's number 105 in the homework. When I made the video, I was on the last edition of the textbook, so it came in as number 97, but it's now in the new edition, it's 105. And so it's in the chapter 3 homework. And so this was a good question that I liked it. So definitely look at that. But the TRO homework is also really, really, really good practice. You got there's so much here. You got practice quizzes, which you've probably already done. You got the credit quiz, but then don't forget about these homework problems too. They're very good to prepare you for the test. And if you want to check your answer, remember I've got my answer key posted. So you can look at if it's a mathematical problem, going to the answer key in the book is not going to be super helpful because it's just going to have the answer. And if you didn't get the same thing, you may not know why. So you can look at my answer key and I've got everything written out for you. So if you have any questions for me, I need maybe like 5 minutes. You can come into the part 2 Zoom session and let me know if you have any questions. But if not, that's it for today. That's all we're doing. So I wish you a great rest of your day. If you've got questions, let me know. If not, Thursday, remember your job is just to take the test. And one other thing, the test is proctored using Respondus. Probably at this point, everybody's used it. If you have not, let me share my screen again here really quick. What I want to make sure you know how to do is where did I put it? I think it's there we go. If you're in course content, towards the end, right above the exam review folder, there's this Respondus practice exam. It has nothing to do with chemistry, but it only is here to help you, like, okay, do the room scan the first time. There's frequently asked questions that Respondus puts on their website. It'll walk you through how to do all of it to get set up, make sure your system's good to go. Can you use an iPad? Yes, but make sure everything's working. Because if it were me, like the last thing I would want is to go to take my test and find out I don't have the right browser, or I don't have the most updated browser, or I've got some issue where it won't work. Anyway, so that's what this is for. Respondus, right? There's a live chat right here. There's a support ticket. If you're having trouble, it needs to be documented. So make sure you reach out to either the Respondus or you call, this is a good number, 341-HELP. That is the IT help desk at SPC, and they are very good about documenting something. So if you are having trouble getting into the test, or maybe your internet goes out during the test, you call the help desk, they can track all that and they'll send me a ticket, and then I get notification and I know exactly what happened. So this is also a very, very, very good number to remember for taking tests online. If you have any questions though, let me know. But again, otherwise, I won't see you back necessarily until Tuesday next week. So I hope you have a great rest of your week. Remember, Thursday, I will be in the Zoom sessions. Like if you need something, just let me know and we can meet. But I won't be there unless somebody asks me to be there. But if you have any questions for me now, just meet me in the part 2. I'll see you then. All right. Have a great rest of your day.